Yes, sure. All right, welcome everyone to our first seminar of the semester. Well, it's my honor to introduce you to Dr. Nichole from Curtin University. Only just because Nichole is very kick-ass scientist in 21st century cosmology, but also, you know, when I was doing my PhD, I was always the senior student that I was always. There you go. That's the
that's the tearjerker. Okay.
Nichole and I have always kind of been traveling across the world counterclockwise. So she started her PhD at the University of Washington with Miguel Morales, and after finishing, she went to Australia, and I kind of moved closer to Melbourne as well. She did a postdoc at Melbourne University, and then now is currently at Curtin University, where I did my PhD, where she's holding the Forrest Fellowship. Nichole's going to talk to us about all the difficulties that you have to deal with when you're trying to analyze real data from radio interferometers in the hopes of finding signals from the first stars in the universe. So with that, I'm just gonna give it to you.
Thank you, Ronnie. Yeah. It's great to be here. It's wonderful to actually do something in person. And I know actually quite a number of people here, so it doesn't really feel too foreign to me. Fun fact before I start, I've actually tried to get job / PhD here twice and been denied twice. So you work at a really great place, and I'm just happy to be visiting, so I can just pretend as if I actually did work here. Yeah, so as Ronnie said, I will be going into some nitty-gritty details about the epoch of reionization and trying to measure it using interferometers. Hopefully I'll stay broad enough that if this isn't your field, you'll still find something useful about interferometers in general. But the epoch of reionization, or the EOR, is a time period in the universe. And you can put the beginning of the universe and the modern day onto this time scale, and I will show you where the epoch of reionization lies in this context. Starting with the Big Bang, you go through the cosmic microwave background, and then you enter a period called the Dark Ages. This is just hydrogen gas floating around, no stars, no galaxies, lasted for about 500 million years. And then over time, gravity coalesces that hydrogen into the very first stars and galaxies. Those first stars and galaxies destroy that from which they come. So they release ionizing radiation that breaks apart protons from electrons in an epoch called the epoch of reionization. It's ionizing the surrounding hydrogen. And that lasts till about 1 billion years or so into the age of the universe. And so from a cosmologist's point of view, this is all the important bits, the early universe. And then after about 1 billion years, you get all the, astrobiology, fun galaxies, all that other stuff for about 13 billion years. So the epoch of reionization is important because it is this last stage of the early universe. It's really the last phase change of the universe. And I'll show a simulation of what it may have looked like. This is from the Dragons team, Paul Gill and Simon Much in particular. In red here, you have neutral hydrogen floating about. You can see it kind of looks like Swiss cheese. That's because you have some white dots distributed in there. Those are the ionizing sources. And once it ionizes that neutral hydrogen, you get this ionized hydrogen in black. And so throughout time, those ionizing sources, as they become more populous and stronger, brighter, start to overlap their ionized regions that we call bubbles. and you start getting different grades of Swiss cheese, if you will, until the entire universe is ionized. So this really is a phase change, and it holds a lot of information. And in particular, that neutral hydrogen holds a lot of bulk information. Sure, you could try to look at the ionizing sources individually to try to understand the bulk properties. But really, if you want to understand the medium, you need to look for the neutral hydrogen. Yeah.
What size, what coordinate box size were you looking at?
Oh, I think that was a gigaparsec.
Really? Was that a simulation done with standard analysis again?
Yes, yes. Yes. That's like one of the bigger ones that I know of. And we ask for bigger and bigger ones every single time. I could be wrong though, so just FYI. The good thing about neutral hydrogen is that it glows. It has a 21 centimeter emission. By the time that reaches Earth, it's in the frequency range of roughly 200 to 60 megahertz or so. So that's roughly in the FM band range, 107.1. So it glows really faintly, however. And so you kind of want to average together, add as much stuff together as possible in order to bring out that signal. And we do that through something called the power spectrum. And this is just a typical power spectrum. Power up here on the bottom that's relative to the cosmic microwave background over time. And so this is really the first stage, the first step. Sure, we would like to image that movie throughout time of the Swiss cheese building up, but this is the first step because we can get more out of the signal this way. And I'm not going to go through each of these parameters, but this is a simulation from Brad and Nichole. And what it really shows is that as you modify the different parameters of the universe, you get different epoch of reionizations, different power spectrums. That's really where the power lies in studying the epoch of reionization. And you can see here, this is kind of an old simulation, but we have some data points here as well. Those are from real data that's looking at high Z stars and galaxies to determine properties. But you can see you can change various aspects of the universe and still fit those data points. So we would really like to look at these bulk properties in order to really nail down these parameters of the universe. It's also kind of a good time period to look at as well, because we know a lot about the cosmic microwave background. We know a lot about the modern day, and we don't know much about the in-between. The epoch of reionization would really help with constraining those models. So we can learn things about cosmology, like what is dark matter, how does it behave, what is dark energy, are there exotic things that we didn't think of? And it can tell us a lot about astrophysics of those first stars and galaxies. How did they form from this pristine, essentially metal-free environment? And what were they? When did they form? And so there are interferometers around the world trying to detect this power spectrum measurement. LOFAR, the low frequency array, based in the Netherlands. The hydrogen epoch of reionization array, HERA, based in South Africa, and the Murchison wide field array, or the MWA, based outside of Perth, essentially. And I nominally work on the MWA. A lot of what I'll show today is MWA specific, but I thought this was fun just to throw up. I helped build part of the instrument. This is me in the outback, assembling stuff. Here at the top here, I'll go into detail about what these things are in a minute, but here's me installing stuff into the receiver box, and then really the brains of the operation, the server room. So interferometers, while the individual elements here are actually quite cheap, the brains are expensive. So here you see Adam. So this is a blast from the past here. Adam and I went and built phase 2 together, which was tons of fun. Each of these things is what we call a bow tie or a spider, just because it looks like that, is a dipole. And you need thousands of dipoles spread out across the Australian desert in order to build up an image. That's what an interferometer requires. Each of these costs about $100. So it's actually, in the grand scheme of things, not very expensive. Great, because you need thousands of them. But again, the thing that really matters here is that server room that costs millions and millions of dollars. The receiver boxes, $1 million each roughly. So this is really where that power lies with interferometers, is in the data processing aspect, not necessarily the dipole electromagnetism aspect. And that'll become important later. I had a really mundane job screwing things in with a drill. That was my contribution. So I mentioned this before, but the epoch of reionization signal, that 21 centimeter signal that we measure on Earth, is really faint. So how faint is it? Well, it's like trying to measure a light bulb on Pluto in the middle of a fully lit stadium. Those are the numbers that roughly work out. And that's because the gas in nearby galaxies also emits in the radio, in the synchrotron emission. And it's roughly 5 orders of magnitude brighter than the signal that we're looking for, which is already faint. But there's one caveat in that gas, that synchrotron emission that we don't care about, has a smooth spectrum. So while the 21 centimeter signal is faint, it has a varying spectrum. So what you can do is you have these foregrounds, galactic foregrounds. This is the synchrotron emission, supernova remnants, free emission, extragalactic foregrounds as well, all of the radio galaxies between you and the EOR, the beginning of the universe, and then finally the EOR signal. And you can actually split these up into slices by taking a Fourier transform, because one has a smooth spectrum, one is varying. And so I will show you a power spectrum today. This is the only type of plot I'm going to show. So no other type of plot will be shown today. So I'll just go through it a little bit in detail. You take Fourier transforms spatially and along the frequency direction. You add it together essentially, and you get this distribution of cosmological structures in Fourier space, or K modes. It's just Fourier transforms. And then you have power here relative on the y-axis. And so larger scale things are more towards the left, smaller scale things more towards the right. And of course, the more of that particular scale size that you've measured, the more you'll have in that particular bin. And so this is what theoretically we had hoped to see when looking for the 21 centimeter power spectrum. All of your foregrounds, super smooth, don't vary as a function of K, would fall right into one bin. Done, easy. The epoch of reionization varies as a function of K, therefore it would populate more modes. So you could just look over here towards the right-hand side of the plot. So that's not what happened. So this is actually what happened. Your instrument itself is chromatic. Essentially what that means is your instrument varies as a function of frequency. This is inherent to the instrument. It's not an error per se. And so what that does is it takes those foregrounds and it artificially modulates them into the other bins. Okay, that's fine. All right. Don't freak out yet, because we still have EOR that we can measure. And so when we talk about trying to measure the 21 centimeter signal, we generally talk about the EOR wedge, which is full of foregrounds and instrumental chromaticity. We don't generally try to look there. And then we also have the EOR window. This is the area that we suspect to be clean. Question, yeah.
How wet is the foreground cosmology?
Not well at all. Yeah. So you have to model everything between you and the EOR at the same precision level that you're trying to measure the EOR at. So it's roughly 1 part in 10 to the 5 that you need to know what these sources are doing. And that in of itself is a giant research project, just studying radio sources in of themselves. I'll try to like talk about some caveats as we get through, but yeah, difficult, not known to the precision that's required. So generally that's why we try to keep to something called the EOR window, to avoid needing a precision required to get down to the wedge. But further on from that, if you try to calibrate your instrument, which you must do, that's a requirement in order to make sure that your scale is right. If you have those errors in the model, you are going to accidentally modulate everything in all the modes from the foregrounds. So your foregrounds, we call it bleeding. You essentially bleed your foregrounds to the right. Essentially what this means is if you try to calibrate as a function of frequency and you make teeny tiny errors as a function of frequency, and then you Fourier transform along frequency, that's going to give you power in all modes. And since the foregrounds are so much brighter than what we're looking for, that immediately means that we can't see the EOR. So this has been known since 2016-ish, and there's been a lot of work done to try to mitigate this. We're definitely making progress. This is definitely the most pessimistic scenario there is. It's definitely a lot better now. But that just kind of gives you the idea of what we're working with in the power spectrum. So really, before I dive into some of the recent research I've been doing, kind of want to give a broad overview of the field in case anyone cares. So this is what the field looked like at roughly the end of 2019. I haven't changed the plot. Great. Yeah. So this is the same type of plot as before, but now color indicates what redshift you're measuring at. So you can choose to measure at a slightly different redshift, and you should get a slightly different power spectrum. So you can see a variety of different points here, but the one I wanted to point out is my own. It's this line here, and I pointed out because it used the same data set as Beardsley 2016, which is the little dipole-esque symbols. And so we decreased our systematics by roughly a factor of 10. And this shows that the systematics, the systematics I'm talking about really are analysis systematics. It has nothing to do with the data. It's purely based off of being spectrally accurate within the analysis itself. This is the battle that we're fighting. But then 2020, 2019 was really a renaissance year for epoch of reionization measurements. We are now much further beyond the limit paper that we published in 2019. But you can see once I start to add where we expect the EOR to be, which is the solid line with the dashed line being roughly a confidence level, where we expect the EOR to be. Right. So still quite a bit off. Hera recently came out with a limit as well. They broke that 10 to the 3 barrier. Still a ways to go though. I will note that putting them all together on this 2D plot with colors is a bit misleading. So I'm going to show you this really cruddy GIF I made of them on the full 3D plot. And I'm doing this because it may seem like a bit of a race between the different interferometers to measure the epoch of reionization, but really what we need is multiple measurements at multiple redshifts in order to extract the cosmological parameters that we're looking for. And so all of this really needs to go down in power in order to really get the science that we're looking for. All right, so that was basically my introduction, overview of the field, what have you. So I'm going to start getting into what I've done, but if there's any other questions, I'm happy to take them. Okay. So As I mentioned before, the analysis, super important. You can get it wrong horribly. Here are just a smattering of what I would consider the most important aspects of a power spectrum analysis. Not going to go through them all, but it kind of helps to have these symbols at hand. I wrote a paper on it. I helped write one of the pipelines. And that's what I will be using today. It's all open source, by the way. You can kind of group these into 3 sets: calibrating procedures, combining procedures, and power spectra. So calibrating, because you must calibrate your instrument in order to get the instrumental parameters correct. Combining, because it's a very small signal, so you need to combine multiple observations together. In fact, you need to combine thousands of observations together. And then finally, making power spectra estimates from that combination. Today, I'll be focusing on the combining aspect. Taking a half a step back, this is what you're measuring with an interferometer. You're actually measuring visibilities. Visibilities are a combination of the beam response, so what the sensitivity of the instrument on the sky intensity, so the point sources, the things that you're measuring, and then a geometric phase term that describes the sampled mode that you've made. So visibilities are neither image space nor fully Fourier space. You get visibilities for every single frequency. So you get it as a function of Fourier mode, and visibility. This is really important because you need to do lots of Fourier transforms. And we can do Fourier transforms of the spatial coherence function, and that reconstructs the image that we would like to see on the sky. So if you want to change your visibilities into something that you can visually look at, you have to take Fourier transforms. And that's fine. Fourier transforms are fine. The issue is that you're measuring millions of visibilities every few minutes, and you need to combine them together efficiently. You could try to Fourier transform twice every single visibility, but it would be difficult. Let's just put it that way. It would definitely not be real time. There is no way that the computer infrastructure that we had even 5 years ago could do this. And so there's a lot of tricks that radio astronomers play in order to combine visibilities together to make images. And what I'm going to show you that it's not all cracked up to be what it is, and we should really think about other things. But the thing that radio astronomers like to do is gridding. So gridding is a verb. You grid your visibilities. Essentially what you do is you take your visibilities, you create a hyper-resolved histogrammed Fourier plane, which I will call UV from here on out. And then you can Fourier transform the U direction and the V direction to get a image of the sky in a certain projection. Essentially, what you do is you create a weighted average histogram in Fourier space. And you do this to avoid having to take tons and tons of Fourier transforms. Now that you have a weighted histogram in Fourier space, you can just take 2 Fourier transforms, boom, image of the sky. In order to do that, you need to know about that A term that I mentioned briefly. This A term is the sensitivity of the beam on the sky, the sensitivity of the instrument looking up. So this is what the MWA would see if, let's say, you were the MWA. If you laid flat on your back in the outback and looked up, you would see this. There's a primary lobe, and then there are side lobes that kind of come off the side of that. What you can do is you can take an FFT of this model of the beam, and then you have what we call a beam kernel in Fourier space. You can take every single visibility, multiply it by that beam kernel, and at the location of every single baseline location in UV space, you can histogram down what that response is. And so this is what a UV plane looks like in Fourier space. This is that weighted histogram, essentially. And if you took a Fourier transform in that direction, you would get an image of the sky. But even further on from that, we know exactly, well, we know how to make maximum likelihoods of these visibilities that we've gridded down. So maximum likelihood is the most likely value for a parameter. And essentially what you want to do is also grid the beam response twice as well. And so you can get sigma squared. This is essentially sigma squared here on the right-hand side. And so you can carry around both of these and make maximum likelihood estimates of the power spectrum. And you get to have propagated errors from here on out.
It's okay.
Yes, please,
So
sir.
the key thing here isn't the left-hand side. I don't care how chromatic your telescope is. If you can perfectly write down the left-hand side, I can get rid of the foreground. The key thing here is what's going on the right side. How well do you know that? Can you say a few words about how you show your beam on the sky, but it looked like a simulation that was pretty symmetric and perfect. So you clearly didn't measure that.
Yeah.
And so that went into what happened on the left. The positions of those antennas, those changes, the season change, the
Yeah.
loads and phases,
Yeah.
whatever.
Yeah.
And then finally you show the error bar on the right.
Yeah.
That error bar on the right is basically how the experiment is.
Yeah.
How good that experiment.
Yeah. Yep. Yep.
Tell me about the right-hand side.
Right-hand side also it does not include covariances as well. That is purely the variance. Right. So this is your estimate of what you expect the errors to be if your instrument is fully operational and exactly where you had put it down, etc.
But how did you get how do you expect that?
How do you expect that?
That is your expectation of how these things are going to move around. And all I care about is something. You did something. You did. How do you
How- Oh, the right-hand side. That is that beam sensitivity twice at each baseline location.
Oh, I'm sorry. Okay, so it's not the error bar on that. It is the square of. Okay, so you have no estimate.
It's the square of the left-hand side without the data. Right.
So
So
you have no estimate on the error bar of that beam and the error.
oh, on the error on the beam. No. We don't have an estimate on the error of the beam, if that's what you're asking, like how well we know the beam. Is that what you're asking?
Yeah, isn't that everything in figuring out how the performance to see filters into your analysis? If you knew your beam first, right?
If I knew my beam perfectly, yeah. No, that's right. Yeah. Bit of a chicken and egg problem, isn't it? If I knew my beam perfectly, I wouldn't need to do these variance stuff, right? I wouldn't have to have an estimate. I would just know it perfectly, calibrate it out, boom, done.
Exactly.
Yeah, no, definitely don't have that. No, 100% not. Right. And that's a lot of research goes into that. I heard Danny was here last week. He does a lot of drone measurements of beams. And it's very complicated stuff, very active research to try to measure what the actual beam is doing. Some people use, I was on a paper that did essentially using communication satellites that you think what the communication satellite is doing. And so you could measure it and get little slices of the beam. And as that communication satellite goes over the course of the year, you can build up a beam model. But do you really know what the communication satellite's doing? Some of them are broken. It's an essentially unsolvable problem to some extent. You will have some error on your beam. I should probably move on. You might be interested in some of the stuff I'm going to show in a minute. There was another question. Okay, cool. Right. So there's enough people in this room who would potentially be able to call me out a little bit I will say this is definitely an optimal map making approach. You could try to, all the stuff I'm about to show, you could try to fix in image space. But once you try to modify stuff in image space, you no longer have nice errors which to propagate because everything is covariant in image space, because that was not the space you measured your visibilities in. You measured visibilities in this space. FYI. Okay. So, okay, we just discussed this. The problem here is that A term is hard. You can't get it right. And the general approach in radio astronomy is to somewhat ignore it. Maybe make it a Gaussian, whatever, what have you. Maybe even ignore it completely. So since we're trying to analyze the epoch of reionization, we need to know more about this A term. Does this affect the power spectrum measurement? Does this affect calibration? And what happens at the horizon in particular? So these are the things that I'll be going over. Here's that instrumental beam image again. Again, I didn't particularly like how cool this was and how perfect it was. So I wanted to test this out in a simulation space. In order to do that analytically, I wanted to decompose this as a series of Gaussians, because when you take the Fourier transform of a Gaussian, it is a Gaussian. You can calculate it analytically rather than relying on some pretty coarse model. This is what my Gaussian decomposition of that beam looks like. It's obviously not perfect, but this is simulation space, and I will just be comparing to this to try to get an estimate for if things go crappy, how crappy can they be? One thing you'll notice here that I'll get into later is that there is no horizon in this image, in this new Gaussian decomposition image, whereas in the real space, there is. So keep that in mind. All right, so I want to make simulations and then test how bad I can have the beam be and still measure the epoch of reionization. So using the symbols that I showed before, this is just going into detail about how I made those simulations, plug them in, test 3 different types of gridding, essentially 3 different types of that combination method. And then I can compare in the power spectrum how bad they look. One thing to note is that the visibilities encode the instrument a priori. So I'm just comparing to that Gaussian decomposition of the beam and saying that's perfect. Everything else I'm doing here in gridding is just comparing to that perfection. So 3 experiments, 3 different beams. Experiment 1, perfect beam, perfect Gaussian decomposition. Experiment 2, I kind of sucked at making the side lobes, which is definitely something that happens. Experiment 3, I don't care about the side lobes. What happens? Just a Gaussian. Here's what those kernels look like in Fourier space. Again, Fourier transform of Gaussian is a Gaussian, so pretty cool. But you also get this Ripley structure. This is essentially a interference pattern. Your side lobes are basically a 2-slit experiment, so you should expect to get ripples. And the thing that's important between these is actually the edge derivative. If you have to cut your beam at some point, right? Especially with the Gaussian decomposition, it's infinite, it's Gaussians. You have to stop gridding. Otherwise, if your beam kernel is so large that you have to grid down through the entire over-resolved UV plane, you might as well have tried to Fourier transform every single visibility from the get-go. So you want to have tiny little kernels to add to your histogram that will make it go faster and log in faster. So here you can see the full width, the single Gaussian has a better edge derivatives given a set of pixels. So you only would need to grid out roughly 10 wavelengths for the single Gaussian versus 30 wavelengths for the Gaussian decomposition to get to roughly the same edge derivative. That's extremely important because we are trying to do this as fast as possible. And so here I have that power as a function of K, EOR wedge on the left, EOR window on the right. Don't necessarily care about the left too much. We would like to be able to measure the EOR on the right. In this light gray that you can barely see, that is the EOR level. I'm not using any epoch of randomization simulation within these simulations. And so if that line, if the colored lines dip down below the gray region, you can measure the EOR there. And so this is just really going through the idea that that derivative matters. Perhaps not the shape so much. Perhaps not our ability to reconstruct that beam image. If I go through each of the various types of beams, you can see that really it does depend on that derivative edge, how much contamination you have towards the right. And this is just plotting all of those together. Essentially, what this means is that simple, small kernels that are smooth as a function of frequency are fine. And you could ask, well, from an optimal map making perspective, aren't you losing signal if you're not using all of the side lobes? You're essentially cutting out portions of the sky by doing that. But you can see here in yellow, I have all three of the different types of kernels, their estimated power, or their estimated noise plotted on top of one another. You can barely tell them apart. So those side lobes don't matter a ton. So if you want to do things quickly, just use a small kernel. I am going to show you that that is actually a false statement, but sure, I can take questions. Yeah.
Just to clarify the setup here, is this your visibility simulation was done the same way for all these experiments? It's just what you're grading within your
That's right.
process.
Just
Okay.
gridding. Yep. Yeah. Question.
Yes. Am I supposed to interpret this as that kind of fireworks around the globe, then the signal that we're looking for?
Within the errors, right? Within the errors that are currently in my pipeline simulation. So you can see some cruddy stuff is happening in the purple down here. That's hitting other errors in my pipeline. But yes, that's essentially correct that we are precise enough to within 5 orders of magnitude for this particular simulation setup. Definitely not true in real life. Yeah. So that was just looking at the combination step. What about if you look at the calibration step? What if you try to use 3 different kernels, 3 different beam images in the calibration step? So how do you calibrate? First of all, will you want to calibrate in visibility space? You can do like a linear least squares using all the different visibilities that you have to get instrumental parameters for each of the dipoles, essentially. There's other ways to do it, I will note, but this is the most common radio interferometer way. So calibrating in visibility space. So you need millions of visibilities to match your millions of data visibilities, but they need to be models, and you need to do it every few minutes in order to calibrate efficiently. So guess what? You can actually do the reverse operation of gridding. It's called degridding. You take a Fourier transform of the sky signal in a certain projection, create a histogrammed, hyper-resolved Fourier plane, and then you can integrate up at every baseline location using your beam kernel of choice, and that will give you a model visibility. Again, just the reverse of the gridding operation. Again, there are better ways to do it. This is the fastest, most common way. And so if your input was, how do I explain this? If you don't, so this simulation was very difficult to run because I decided to do it semi-analytically. You'll see in a second why. Essentially, what I'm saying is that avoid histogramming at all costs and calculate at every single data point that you require, avoiding the histogramming operation, essentially. If everything is semi-analytic in the input and the experiment itself was semi-analytic, aka you matched it, and you have the perfect kernel, then of course it looks great, even if you calibrate. The second you use a non-instrumental beam kernel, as in like you didn't get your side lobes right in yellow or red, you just completely ignored your side lobes, you can see that you have significant contamination towards the right. This means that the EOR is not measurable in this particular instance. This is not necessarily new per se. For the eagle-eyed people out there, this is essentially the same simulation as I showed at the very beginning when I was trying to describe what a power spectrum was. The thing that really surprised me about this is that the yellow line is so bad. The yellow line is if I didn't get my side lobes quite right. Essentially, I made my side lobes half the power what they should be. Side lobes are down 5% at the 5% beam sensitivity level anyways, so it's really small errors. And I'm not terribly confident in the models that we make even being close to that. What's even worse is that if you actually use gridding operations, if you actually histogram stuff together, which is required in order to do things in the Hubble time, even if you had a perfect kernel, you would get this green line. So that means even in the best of circumstances, we can't measure the EOR using the degridding operations that are so common in radio science, radio interferometry. Okay. I should go maybe a teeny bit faster, but really quickly, I think this is actually the most important bit for the MWA stuff. Is what if I do actually include a horizon? So I've just now put in a horizon here in my visibilities. I can do that because the horizon is essentially a cylindrical top hat. I know what that is analytically Fourier transform wise. It just means I have to do a convolution, which really took a long time. A perfect convolution. Anyways, none of that like Fourier transform convolution stuff. So if you add a horizon here at the very edge of that Gaussian decomposition, you get this beam kernel here on the right, and it is infinitely extended. That is the issue, is that it ripples at a significant level forever. So that means if you have measurement, no measurement, you have a hard edge will ripple in Fourier space forever. That's essentially what this means. So you can see here, you can barely measure the epoch of reionization if you had an infinitely extended kernel. There's definitely debate on whether or not that's actually true. It's not. There should be some nice curved edge based off of like the depth of the soil and if it's wet and if there's a bush. But we don't actually go into that level of detail, obviously. And the simulations that model the beam really can't achieve that level. This is just showing that if you Fourier transformed, instead of doing an analytic convolution of the beam kernel, you obviously get some extra spectral damage towards the right. One thing to note is if you have no side lobes, if you have no interaction with the horizon, then you are going to hit a nice deep baseline on the right regardless, because you don't have any infinitely extended ripples. That's really the point of that. And that's just saying future instruments might be nice to not have interactions with the horizon. And I will say these interactions, like at the top here with the Gaussian decomposition, we're talking roughly 0.3% level of sensitivity at the horizon can create this monster that we see. So published a paper on that among Choksi, detailing each of those three aspects of gridding, calibrating, and what happens when you have horizon-based effects. So now I kind of want to show what I've been doing very, very recently, doing this, applying these lessons to data. I don't have any more plots to show you, so you can don't have to worry about that. I only have images. So here is an image of the MWA uniformly weighted residual, just looking at the primary lobe. It looks very coarse and gross, right? That's fine because I've subtracted most all of the point sources, so it doesn't look like the night sky that you would see. This is essentially removing all the point sources of the night sky. This is what the beam looked like. Oh, this is the using the FFT of the beam model as before, and this is using that Gaussian decomposition of the beam that we have now. You can see just by eye how much nicer those beam edges are. I think those beam edges are at 5% beam sensitivity level. And in this image, you can almost kind of see like this diffuse ripple-y structure in the background. There should be some diffuse synchrotron emission from our own galaxy in the way, so that's kind of nice to see. But if we extend out to the horizon in the east-west direction, you can see a really bright thing towards the west. And that's actually the galactic plane. So we take our measurements to try to avoid this beast because it is, we know it will be an issue. But in doing so, I think we kind of shot ourselves in the foot because the galactic plane is just rising here. And in this residual image, it is by far the brightest thing on the sky. Again, at, this is getting close to the 5% beam level. It is still the brightest thing. What's even worse is that it aliases because it is at the edge of the horizon. So this is inherent. This isn't something that's like, it's not like the analysis went wrong per se. It's just because you are measuring something so bright and all of a sudden you're not measuring anything at all, or you slowly taper off, what have you, whatever your poison is, it's still going to be a hard edge. It will alias. So our model needs to include the galactic plane in order to measure the EOR. That's Jack there. He made a wonderful thing called Woden. It's a GPU visibility simulator. So instead of using degridding, which I just showed was terrible, Jack made a GPU-based visibility simulator that actually does each of the computations analytically. And it uses Chris Jordan's hyper beam, which allows it to include that A term as effectively as possible. It still takes a ton of resources to actually get anything out of this, especially if you're doing the galactic plane, which is a huge swath of sky. But just to give you a little taster, this is what it looks like when you subtract that galactic plane. You can see the galactic plane disappearing as well, but if you kind of unfocus your eyes and look, you can see that the aliasing is happening throughout the entirety of the image at a very low level. And this is a continuum image as well. I combined all the frequencies together to make this. If you did this as a function of frequency, a frequency slice, you can see that aliasing is actually going to happen at different locations. Something that moves as a function of frequency, take a Fourier transform of it, it's going to have contamination in the power spectrum. So this is really where we're focusing our efforts now to try to remove this galactic contribution at the horizon level. So in summary, we'd really like to measure the EOR because it's full of information we'd like to know. But obviously the traditional radio astronomy techniques that we've used for such a long time need to be reevaluated through an EOR lens. If you want more information, Barry and Chokshi 2022 in AppJ. And maybe there is a new limit on the horizon. You see what I did there? All right, thanks, I'll stop.
For the horizon program, how low does the side loads need to be before we can?
I know, yeah, I think I calculated it at 0.3% to hit the EOR level. Obviously, it would be better if it was even lower than that, but I didn't go into great detail because like I mentioned, there is kind of this idea that even though the models of the beam that we have are very like measurement, boom, no measurement at the horizon, there should be a soft tapering depending on the soil content, but that's not something that has been modeled. It's very difficult for FECO simulations, the electromagnetic simulations, to include anything that doesn't have an infinite ground plane. So we're kind of battling that at the moment.
And is that assuming the galaxies on the horizon or like field dependent?
That is very true. It is very field dependent. So that's why I said like we shot ourselves in the foot. We put the galaxy at perhaps a very terrible location. There are other observations that where it's not on the horizon, but there's other terrible gross stuff that happens, really bright galaxies that you have to look subtract those. Effectively, it's a pick your poison situation. Yeah.
John?
First, what Pulsar said,
Say that again.
what Pulsar said, to try and get an estimate of the beams actually on the horizon.
Oh, no, have not. That's essentially what the communication satellites are trying to do. Is getting basically a slice of what's happening. The pulsars, that might be a really good idea. Because it's always going to be aimed at you, I guess. We definitely failed with the communication satellites because they're not beaming at you as they set. And so you're going to have a different response. So you have to like try to backtrack that. And it's been too difficult. Pulsars may be the way to go. You might not be able to get it all the way around, but you might be able to get an idea.
I mean, you can get an idea.
Get an idea. Yeah, it's a great idea. Yeah.
I was gonna ask, our covariance is just too expensive to compute? Because
Yeah, no, you can't.
if you want to call it next to mine, like really do the calculus.
Yeah.
It's also-
Yeah. You totally can. Definitely has been done a ton. Adrian has done it plenty. It's expensive. This is definitely from the point of view of like quick and dirty traditional radio astronomy.
But it might give you a way down the horizon too. I don't know if that works or not. But you can say the horizon's very noisy once you stick with covariances.
Sure. Yeah, that's true. And the thing is calibrating. That's the thing that's going to suck. Right.
It always does.
Yeah, that's the thing that sucks. Sure. So like I showed with the just using the variances, there was essentially no change in the noise by choosing a smaller beam kernel and just saying screw it to the other stuff. That's essentially getting at the same idea, is that with gridding you can force it at the consequence of noise, but that doesn't solve the calibrating problem.
Yeah, some more questions about math first.
Yeah, so, the question about how low the silos need to be before you don't need to know that, like 0.3%. Isn't that, couldn't that question be rephrased, is how well do you need to know the silos?
Yeah. Yep.
And I guess that comes back to John's question about pulsar, where finally you may be able to see something in the far silos because you're turning the sky on and off, where the communication satellites not just suffer from the beating problem, but they suffer tremendously from the confusion of knowing where that light's actually coming from.
Yeah, and sometimes they emit at frequencies that you did not tell them to. Yeah. Yeah.
Something very close.
Yeah, they are not for science. Yeah, the pulsars is a great idea. Again, like with the precision-based aspect, like I showed with the half power side lobes trying to calibrate with them, like that wasn't even a horizon problem and it still was terrible. So that's the level at which we need to know the beam, which is not going to happen.
Great. So I shouldn't think of that. I think anyone needs to go with also 0.3% of
side lobes, but rather that everyone needs to post oaks where they know their side oaks better than 3%, and the next load and the next load after that.
Sure. Sure, I'd still prefer an instrument with no side lobes, but that's obviously extremely difficult to manage. Yeah, yeah, so yeah. I agree with you.
And at what level- so there's no the instrument response, the full beat pattern.
Mhm.
So you actually have that. Or do what we're doing right now, which is zero it out. It's another way of saying, the airbox.
Yeah,
How long do we, so you're calibrating also from the sky itself,
yes,
and of course, the degree to which I need to know my side lobes.
Yes.
The degree to which there are bright intervals that I.
yes,
Maybe over, even though the 0.3% side lobe over here. Pass A would be 10 million brighter than that.
right, right.
So how well do we, there's a question that I'm hoping that well, there's also the question of we've got to learn the sky better.
Yes,
So that we can calibrate from it.
that's right.
Especially like is that how bad is that?
It's bad. It's very bad. So
Variability, the position.
it's spectral. It's the spectralness of it. You can get everything wrong by 2. That would kind of suck, but at least your power spectrum would still be smooth, if that makes sense. It's trying to get it as a function of frequency that's very difficult.
I don't think you're not stating possibly. If you don't know the intensity of this source
Yeah,
with respect to that source, then the chromaticity of your beam, the side lobes, the relative level of those.
Oh.
lines turn together. And so I think.
Yes.
You must need to know both of these.
yeah. Essentially, what you're saying essentially is that, like, let's say you know about this source, and let's say you don't know about this source. This source has a PSF that varies as a function of frequency. It's going to actually modulate the brightness of this source as that PSF changes as a function of frequency, and so you're modulating.
So one of our challenges is that all these sources we look up in the literature and are measured with other telescopes that have chromaticity.
Yeah.
It's too much.
Yeah. Right. So there's other ways you can try to get around the calibration problem. In fact, a whole slew of literature. Hera tries to use redundant baselines to not have to use the sky. Essentially, you measure the same thing over and over and over again. You have a system of equations. You could just get out the parameters of the instruments. Unfortunately, that still depends on the sky, because when you do redundant calibration, there are parameters you cannot solve for. That are get the word I'm looking for. What? Degenerate, thank you. They're degenerate, so you have to use the sky anyways. So you still get those chromaticity issues, and it still comes in. One thing I like to do, which is all right. I don't know if it's going to be any better or worse, but this is the thing that we play with. Is I use the auto correlations to do calibration instead. So instead of using cross correlations, one tile correlated with itself to give it visibility, I use a tile correlated with its own self. The issue with that is that you're correlating the noise as well. But that's far less of an issue, it seems, than all of the other stuff that I've just been talking about. Yeah, so it seems to help. With the MWA, very instrument specific. Very instrument specific, yeah.
Final question goes to Vicky before we close off.
Well, listening to this whole conversation and as someone who's not in the field, the impression I'm getting, which may not be the one you intended to give, is that those terms is really hard and bordering on not possible. But maybe that's not what you meant to say.
Well, philosophically, I think you have to be a bit of a pessimist to go into EOR field. I think we're all kind of like this. But or hyper optimist, yeah, it swings both ways. Yeah. Look, it's not impossible. It's just every single thing that we thought was going to be easy hasn't been. And we're just mad about it. I think it's possible eventually.
Do you want to make it more optimistic?
I just want to make a comment that I think the measurements of these points versus on the sky, their spectrum is super important. And all of us that are doing measurements of different frequencies are using historic catalogs. For people who don't care.
Right. Yeah.
Someday in the future, there may be a time when those experiments, they care, they want to pull observe and so forth, our bands don't go out, so they're going to help each other.
Right.
But we aren't possibly going to understand the sky and put up our calibrators if we don't also understand the error bars on the source, how well we know. And we
Yeah.
certainly want to
For sure. For sure.
So we're just waiting for these bats of people to catch up to us.
No, I think we have to be different.
I mean, we're throwing caution to the wind and saying,
Yeah.
I need something better. Will someone save me? Yeah.
All right, on that note, thank you, Nichole, again.
Thanks.
And if you're interested in joining us for dinner, we're not having the seminar speaker dinner today, we're doing it on Thursday, so it's still time to clear up your calendar and, tell your family you won't be home. And contact me if you want to.
Thanks, Ronnie.
Yeah, no. Birthday.
Hi.
I'm Zarif. I'm grad student.
Oh, okay, great. Yeah. Yeah. Thanks for grabbing me.
Yeah, or